Okay, in this lecture we're going to cover our section 2.3 material on volume by cylindrical shells. And the idea in this section is to determine the volume of a solid of revolution where maybe the disk or the washer methods aren't possible, or at least wouldn't be very easy. So to motivate the problem that we're going to be considering throughout this section, let's pose the following question. Suppose that f is some continuous function such that f of x is non-negative for all x in some interval from a to b. So that is the graph of this function f of x lies above the x-axis within that interval. And our question is, what would be the volume of the solid obtained by revolving that region under the graph of y equals f of x for values of x between a and b about the y-axis. So we were asking a similar question in our previous section. What would happen if we revolved this region about the x-axis? And we saw that we could use the disk method to calculate that volume. Now, if we're revolving about the y-axis, well, it might become a little more complicated. So let's see if we can visualize what we're trying to do here. So we have in the xy plane the graph of some function y equals f of x, which is non-negative, so our graph lies above the x-axis. And we're looking at the region under the graph of this function and above the x-axis on the x interval from a to b. So we're going to take this shaded region, and I want to revolve that region about the y-axis and determine the volume of the solid that I would get. So in order to do this, well, let's think about a similar approach to what we were doing in our last section. So for this region under the graph of a function of x, we can think about taking a little representative slice through our region at a point x between a and b along the x-axis. And let's call the thickness of this slice dx, a differential of x. So if we take this little vertical strip or slice and we revolve it about the vertical line, the y-axis, or x equals 0, let's think about what sort of shape we would get. So taking a little vertical slice and revolving about a vertical axis, we end up getting a cylinder shape, which is hollowed out through the middle. So the thickness of this little cylinder, or hollowed out cylinder, which is called the cylindrical shell, is dx. Now our goal is to find the volume of this cylindrical shell, and if we can find the volume of this shell, then we could add up the volumes of all of these shells as x ranges from a to b by using a definite integral, and that would give us the total volume that we're interested in. So let's think about how to find the volume of this cylindrical shell. So to visualize this, let's think about taking this shell and cutting it along some edge here. So if I were to slice this through and unroll my cylindrical shell, I would have a little rectangular prism of a thin thickness, let's call it dx. It's like the thickness of the wall of this shell. And we need to find the volume of this little rectangular prism. Well, we know its thickness is dx. Let's see if we can find its height. So the height of our rectangular prism, let me maybe use a different color here, would be the same height along our cylinder, which, looking at our figure, would be the height of this representative strip that I was taking. So for any point where I take this slice, the height of this strip is defined by the graph of my function, y equals f of x. So the height of this little rectangular prism, which is the same as the height of my cylindrical shell, will be f of x, whatever the value of the function is at the point x where I'm taking my slice. And then let's think about how to find the length along this edge. So this little rectangular prism was obtained by slicing my cylindrical shell and unrolling it. So the distance along the bottom of this rectangular prism will be the same as the distance around my cylindrical shell, or in other words, its radius. So I would have 2 pi, or its circumference. So I would have 2 pi times the radius of this cylinder R. Now let's think about what the radius is going to be. So the radius is going to be the distance from the center of my cylinder to this outer edge. So the center of our cylinder is at the axis of revolution, in this case, our y-axis. And this horizontal distance that I was moving out to the edge of my cylinder is what we were calling x. So that would be the radius of my cylinder here. So the circumference of that cylinder, or the length along the bottom of this little rectangular prism, would be 2 pi times x. So now the volume of this little cylindrical shell will be a differential of the total volume that I want to find. I'm going to call it dV. And it's found by taking the length along the bottom of our little rectangular prism, which would be 2 pi x, times its height, which was given by the function f of x, times its thickness, which is what we were calling dx. And now to get the total volume for this solid of revolution, well, I want to add up the volumes of all of these little cylindrical shell sections that I got. And I can do that by integrating this differential of volume for all values of x, ranging from x equals a, which was the left edge of my region, up to x equals b. So this formula that we've derived is summarizing what's called the method of cylindrical shells. So to make this a little more precise, let's state it as follows. If R is the region under the curve y equals f of x on the x interval from a to b, then the volume of the solid obtained by revolving that region R about the y-axis is given by the integral from x equals a to b of 2 pi times x times f of x dx. And of course, that constant 2 pi I can bring out in front of my definite integral. So this gives us another technique for determining the volume of a solid of revolution, where our region might be more easily sliced with a little vertical strip, and we're revolving about a vertical axis. Or we'll also see some examples where it might be easier to slice our region bounded by the curves with a horizontal slice, and we want to revolve around a horizontal line. So in the case that you're taking a vertical slice or a horizontal slice, and you're revolving about an axis, which is also a vertical line or a horizontal line, you're going to make use of this shell method, or the method of cylindrical shells. So to get a little more familiar with this method, let's look at some examples. In our first problem, we're asked to find the volume of the solid obtained by revolving the region bounded by y equals 1 over x, y equals 0, which is the x-axis, and the lines x equals 1 and x equals 4 about the y-axis. So as with our previous section, we know that it typically helps to visualize our region. So let's start by sketching this. So in the xy plane, we're looking at the region bounded by y equals 1 over x. So in the first quadrant, y equals 1 over x, looks like this. The x-axis, which is already shown, and then the vertical lines x equals 1. So here, if this curve is y equals 1 over x and x is 1, the y value would also be 1. And the vertical line x equals 4, in which case our y value would be 1 over 4. So we're looking at this little shaded region under the graph of y equals 1 over x from x equals 1 to 4, and we want to revolve this region about the y-axis. So let's think about this. Looking at our region, it seems like it would be easier to slice up this region with little vertical strips of a thin width dx taken at a distance x from the y-axis between 1 and 4. And we can see that if we're going to revolve a vertical strip about a vertical axis, we would get a shell shape for that little solid of revolution there. So that suggests we're going to be using the shell method. So I'll say using shells. The volume of this solid would be found by integrating 2 pi times the radius of our cylinder, which would be the distance from our axis of revolution to our strip, which is x, times the height of our cylinder, which is given by the function 1 over x, times the thickness of our little cylinder, which is what we were calling dx, and we're integrating here over the x interval from 1 to 4. So we can see here, well, this simplifies pretty easily. We have 2 pi times the integral from 1 to 4. The x times 1 over x leaves us with 1 dx. So we have, for an antiderivative, 2 pi times x, and we're evaluating from 1 to 4. So we have our constant 2 pi out in front. When we evaluate x at 4, we have 4. Subtracting the value we get when we evaluate at x equals 1, we have 1. So we're left with 2 pi times 3, or 6 pi cubic units for the volume of the solid being described here. All right. So let's look at some other ones. In this next example, we're asked to find the volume of the solid obtained by revolving the region bounded by y, which is x minus x squared, and the line y equals 0, which is the x-axis, about the y-axis. So again, our first step might be to try to sketch the region of interest, which is a region bounded by 2 curves here. So to sketch this, let's start by maybe finding their points of intersection. We're going to set the equations for these 2 curves equal to one another. That is, x minus x squared will be equal to 0. And now to solve for x, well, I can factor out an x from the expression on this left-hand side, which would leave me with 1 minus x is 0. So it follows that either x is 0 or x is 1. So let's see if we can sketch this. We have in the xy plane, one of our curves bounding this region was the x-axis, which is already shown. And let's see if we can find the points of intersection with our other curves. So we had x equals 0, so y is also 0, and x equals 1. And our other curve was y equals x minus x squared, which is a quadratic in terms of x, which has a negative x squared coefficient. So in general, the curve is shaped like a downward opening parabola. So it looks something like this. So my region of interest is this shaded region shown here. So this curve is x minus x squared. We had the x-axis as the lower bound, and the intercepts were at x equals 0 and 1. So we want to take this region and revolve about the y-axis and determine the volume of the resulting solid. So looking at this region, we can see, since it's bounded by functions of x, it would probably be easiest to slice up this region into little vertical slices, taken at a distance of x from the y-axis, where x is somewhere between 0 and 1, of a thin thickness dx. So we can see if we take this vertical strip and we're revolving about a vertical line, we would have a shell for the resulting solid of revolution. So that means we're going to be using the method of cylindrical shells, or the shell method. And our volume of this solid of revolution would be given by 2 pi times the integral along the x-axis here from 0 to 1 of the radius of our cylinder, which we already said was x, the distance from the y-axis out to our strip. And the height of our cylinder is given by the height of this slice that we're taking, which we can see is given by the function x minus x squared times the thickness of our cylindrical shell, which is dx. So in order to evaluate this, let's start by distributing the factor of x inside of our integral. So we have 2 pi, the integral from 0 to 1 of x squared minus x cubed dx. So for an antiderivative, we have 2 pi times a 1/3 x cubed minus 1/4 x to the 4th. And we're evaluating from x equals 0 to 1. So that gives us a constant 2 pi out in front. Evaluating this antiderivative at x equals 1, we have 1/3 minus 1/4. We subtract what we get when we evaluate at x equals 0, which would be 0. So we're left with 2 pi times 1/3 minus 1/4 is 1/12. So altogether we have pi over 6 for cubic units for the volume of the solid being described here. Okay. So let's look at another example. This next one's a little bit different because we'll be revolving about the x-axis, but we'll see that the region being described would be more easily sliced using horizontal slices instead of vertical slices. So here we're asked to find the volume of the solid find the volume of the solid obtained by revolving the region bounded by x equals y squared, x equals 0, which is the y-axis, and the horizontal lines y equals 2 and y equals 5 about the x-axis. Okay, so let's see if we can sketch this region. We have in the xy plane, the region bounded by the parabola x equals y squared, which is a parabola opening along the positive x-axis. Here we're only interested in the upper half of this parabola. Let's see y. So our other bounds for this region are x equals 0, which is the y-axis. And then the horizontal lines at y equals 2 and y equals 5. So this is why we're only interested in that upper half parabola. If we were to draw the lower half, well, we see it doesn't affect the region that we're interested in, which is the shaded region shown here. Now looking at that shaded region, we can see pretty quickly that it would be more easily sliced into horizontal slices as opposed to vertical slices. So here we can take a representative slice through our shaded region at a height of y units above the x-axis and of a thin thickness, dy, a small distance along the y-axis is what we would call that differential of y. And we're going to revolve this about the x-axis. So if we're taking a horizontal slice and we're revolving it about a horizontal line, then we could see we would get a shell shape for that cross-section. So using the shell method, the volume of this solid would be given by 2 pi times the integral along the y-axis from 2 to 5 of the radius of my cylinder, which we said is the distance from our axis of revolution out to the strip, which we were calling y, how far we've moved from the x-axis. In the vertical direction is y. And then the height of our cylinder would be given by the length of this slice, this little red strip that we've taken. So we can see that the horizontal distance we would move from the y-axis out to the edge is defined by this curve, which was x equals y squared. So if we take a slice at a height y, then our length of that cylinder, the height of that cylinder, would be y squared times the thickness of that cylinder, which is dy. So we now have 2 pi times the integral from 2 to 5 of y cubed dy. So for an antiderivative, we have the constant 2 pi times a 1/4 y to the 4th, and we're evaluating from 2 to 5. So simplifying a little bit here, well, we have a constant 2 pi times the 1/4 gives us pi over 2, times when we evaluate this antiderivative at 5, we would have 5 to the 4th, or 25 squared, which is 625, minus 2 to the 4th power, which is 16. So altogether, we're left with 609 pi over 2 cubic units for the volume of the solid being described here. All right. So a few introductory examples for this method of cylindrical shells, or sometimes just called the shell method for short. Now in these next couple of examples that we'll look at, we'll see that the shell method might become a little more complicated if our axis of revolution is not necessarily the x or the y axis, but maybe an arbitrary horizontal or vertical line. Or if we're looking at a region bounded between the graphs of two functions instead of by a function and the x or y axis. So let's look at some examples of this. This first one, we're asked to find the volume of the solid obtained by revolving the region bounded by y equals x squared, y equals 0, or the x-axis, and the vertical lines x equal 1 and x equal 2 about the line x equals 3. So let's sketch our region to help us visualize this problem. So here we're looking at the region bounded by the parabola y equals x squared. So that is a parabola whose vertex is at the origin, opening upward. The line y equals 0, which is the x-axis already shown. And then the vertical lines at x equals 1, so our corresponding y value would also be 1. And when x is equal to 2, in which case our y value, 2 squared, would be 4. So we're looking at this shaded region. And here we're told that we want to revolve about the line x equals 3. So let me clean this up a little bit. My curve was y equals x squared, and we're looking at an axis of revolution being this vertical line, x equals 3. So this is the line that we want to revolve about. So looking at our shaded region shown in this problem, we can see that it would be more easily sliced into little vertical slices, where we would take this slice at a value x, or at a distance of x units along the x-axis, somewhere between 1 and 2. And the thickness of this little slice we're going to call dx. So if we look at our representative strip, or our slice here, and we revolve that strip about the line x equals 3, well, revolving a vertical slice around a vertical line, we're going to get a shell shape for our cross-section. So we're going to be making use of the shell method. So let me start by saying using shells, the volume of this solid is given by 2 pi times the integral along the x-axis here from 1 to 2 of the radius of our cylinder. So we have to be a little bit careful in determining the radius of our cylinder if our axis of revolution is not the x or y axis. So let's think about what the radius of our cylinder is going to be here. So the radius, let me maybe sketch this down here. So we're going to have a little cylindrical shell of a thin thickness dx. And of course, the height of this cylinder is given by the curve y equals x squared. But now the radius is the tricky part. Let's think about visualizing our radius. So the radius is going to be the distance from the center of our cylinder to the outer edge. So if we're revolving about the line x equals 3, the center of our cylinder is going to be a point on that line. Now the The question is, what is the distance from that center, or our axis of revolution, to this outer edge? Now we know that the total distance from the y-axis to the line x equals 3 would be 3 units. And the distance from the x-axis out to where we were taking our slice was x units. So the remaining distance, which would be the radius of our cylinder here, would be the difference in those values. So here the radius of our cylinder is going to be 3 minus x. So for our integral, using the shell method, we have 2 pi times the radius of our cylinder, which is now given by 3 minus x, times the height of our cylinder, which we said is x squared, times its thickness, which is what we were calling dx. So once we have this integral set up, in order to evaluate it, we can distribute the x squared. So we have 2 pi times the integral from 1 to 2 of 3x squared minus x cubed dx. So for an antiderivative, we have 2 pi times an x cubed minus 1/4 x to the 4th, which we're evaluating from 1 to 2. So let's see what this leaves us with. We have out in front a constant 2 pi, and when we evaluate this antiderivative at x equals 2, we have 2 cubed, which is 8, minus 2 to the 4th, which is 16 times 1/4 is 4. And then we subtract what we get when we evaluate at x equals 1, which would be 1 minus 1/4. So we're left with 2 pi times the 8 minus 4 gives us 4. And then we were subtracting 1 minus 1/4, which is 3/4. So inside of the parentheses, our 4 minus 3/4 is 13/4. Multiplying by 2 pi would give us 26 pi over 4, or 13 pi over 2 cubic units for the volume of this solid being described. Okay. So we see in this example, it's a little bit trickier in the case that our axis of revolution is not just the x or y axis, because in those cases, the radius of our cylinder was either x or y. But if we're revolving about another vertical or horizontal line, our radius for the cylinder might be some function of x. So let's take a look at another one. In this next example, we're asked to find the volume of the solid obtained by revolving the region bounded by y equals the square root of x and y equals x squared about the vertical line x equals -1. So let's start by sketching our region here. So in the xy plane, we're looking at the region bounded by y equals the square root of x, which would be the parabola opening along the positive x-axis, in particular the upper half of that parabola, since y is the positive square root of x, and y equals x squared, which is the parabola opening upward, whose vertex is at the origin. And these intersect, of course, at the origin, 0, 0, and at the point where x equals 1 and y equals 1. So our region of interest is this shaded region between those two curves. And we want to revolve that region about the vertical line x equals -1. So if we were to think about slicing this region up into slices, well, we see the region is bounded by two functions of x. So it might be easy to think about our region sliced into vertical slices, where our slice is taken at a distance or at a point x along the x-axis somewhere between 0 and 1, and has a thin thickness dx. So we can see if we were to revolve that little slice about the vertical line, x equals -1, we would have a cylindrical shell shape. So we're going to be using the method of shells here. So let me say using shells. The volume for this solid would be found by taking 2 pi times the integral along the x-axis from 0 to 1 here of the radius of our cylinder. So let's think about this. Again, visualizing, it might help to sketch the little shell shape that we're going to have. So we have our little cylindrical shell of a thin width dx. Now let's think about the radius of this cylinder. So the radius of this cylinder will be the distance from its center to the outer edge. Now the center of our cylindrical shell will be at this axis of revolution at x equals -1. And we're interested in the distance from that center out to this slice. Now we know that the distance from our axis of revolution, which was x equals -1, to the y-axis would be 1 unit. And then the distance from the y-axis out to our slice is what we were calling x. So the radius of our cylinder here is going to be 1 plus x. And now let's think about the height of our cylinder. So the height of this cylinder is going to be given by the height of our strip here, which is bounded above and below by two functions. So the height, or the distance between those curves, is going to be given by the difference in the upper curve, which was y equals the square root of x, minus the lower curve, which was y equals x squared. So using this shell method, we had our 2 pi times the radius of the cylinder, which we found to be 1 plus x, times the height of the cylinder, which is root x minus x squared, times its width, dx. So in order to evaluate this integral, we need to expand. So we have a constant 2 pi times the integral from 0 to 1 of, if we expand this, we would have the square root of x minus x squared plus x times the square root of x is x to the 3/2, and then minus x times x squared is x cubed dx. So let's find our antiderivative. We have a 2 pi times the antiderivative of the square root of x would be 2/3 x to the 3/2 minus the antiderivative of x squared would be 1/3 x cubed plus the antiderivative of x to the 3/2 is 2/5 x to the 5/2, and then minus the antiderivative of x cubed is 1/4 x to the 4th, and the whole thing is being evaluated from x equals 0 to 1. So let's see what we get. We have a constant 2 pi times, evaluating at 1, gives us a 2/3 minus 1/3, plus 2/5 minus 1/4, and then subtracting what we get when we evaluate at x equals 0. Well, when x is 0, we have 0. So simplifying a little bit, we have a 2 pi times the 2/3 minus 1/3 gives us 1/3 plus 2/5 minus 1/4. So here, after some simplification, we can find that we're left with a total of 29 pi all over 30. So here, to combine those fractional terms, you can use a common denominator of, say, 60. And after some simplification, you're left with 29 pi over 30 cubic units for the volume of that solid being described. So again, the point I'm trying to stress with these two examples is that if our axis of revolution is not either the x or the y-axis, then we have to be a little bit careful when we're finding the expression for the radius of our cylindrical shell. Now, to finish out this section, we're going to talk about some problems involving volumes of solids of revolution where more than one method would be possible. So we've talked about a few different methods in this chapter so far. We had the method of cross sections, the disk method, the shell method, and the washer method. And there are certain solids of revolution for which more than one method is possible. So we're going to look at some examples which compare the different methods that we've discussed and see that those methods would yield the same volume. So in this next example, we're asked to consider the region R bounded by y equals x squared and y equals 2x. And we're told to set up but do not evaluate integrals to find the volume of the solid obtained by revolving that region R about the x-axis using the washer method and the shell method. So as with our earlier examples, our first step might be to find the or to sketch this region, which is a region bounded by two curves, so we might want to find their points of intersection first. So here, let's set the equations for these two functions equal to one another. That is, x squared is equal to 2x. So it follows that x squared minus 2x is 0. Or factoring out an x, we're left with x times x minus 2 is 0. And so x is either 0 or 2. So let's sketch our region here. We have two curves that we're intersecting at x equals 0. So to find the y-coordinate, well, y is x squared, so 0 squared gives us 0. And at x equals 2, where y would be 2 squared or 4. Let me draw this a little better to scale. So if this is x equals 2, my y value would be 2 squared or 4. So the two curves that we had were y equals x squared, so this parabola opening upward, passing through these 2 points, and then y equals 2x, which would be the line passing through those 2 points. So here our lower curve was y equals x squared, the upper curve was y equals 2x. So we're supposed to revolve this region about the x-axis, and we're supposed to set up integrals for the volume of the resulting solid in two ways, using the washer method and the shell method. So let's take a look at this. If I were to slice this region into little vertical slices, taken at a distance x, somewhere between 0 and 2 along the x-axis, of a thin width dx. Well, I can see when I revolve this vertical strip about the horizontal line, y equals 0, or the x-axis, that I would have a washer shape. So I'll start by saying, using the washer method, I could calculate the volume as pi times the integral along the x-axis from 0 to 2 of the outer radius of my washer, which would be the distance from the x-axis to the top curve, which was y equals 2x. So I take that outer radius squared, and then I subtract the inner radius for my washer, which is the distance from the x-axis to the lower curve, which was y equals x squared, and I square that inner radius, multiply by the thickness of my washer, which is dx. So simplifying just a little bit, we have pi times the integral from 0 to 2 of 2x quantity squared gives us 4x squared, minus x squared is x to the 4th dx. So this would be an expression for the volume of that solid using the washer method. And here we don't need to evaluate that integral. We were told to just set up this integral, but do not evaluate it. Now we were also supposed to find an integral which would make use of the shell method. So if I'm revolving about a horizontal line and I want to use the shell method, that means that I need to consider a horizontal slice through my region, taken at a distance y along the y-axis, somewhere between 0 and 4, of a thin thickness dy. So let's see if we can set this up using shells. So the volume of our solid using the shell method would be given by 2 pi times the integral along the y-axis from 0 to 4 of the radius of my cylinder, which would be the distance from the x-axis up to my strip, which is what we were calling y, times the height of my cylinder, which is going to be the length along this little blue rectangle. Now we can see here that that slice is bounded on the right-hand side by this parabola, and on the left-hand side by the line shown here. But if we're integrating with respect to y, we need the equations for those two curves to be functions of y instead of x. So let's look at the equations for those two curves and solve for x. So for our parabola, we had y equals x squared, or equivalently, x is the square root of y. And for the line y equals 2x, we have x is equal to y over 2. So the length along this little blue slice, which would be the height of our cylinder, is given by the equation for the rightmost curve, which was x equals the square root of y, minus the equation for the leftmost curve, which was x equals y over 2, and then we're multiplying by the thickness of our cylinder, which was dy. So simplifying a little bit, we have a 2 pi times the integral from 0 to 4 of distributing the y times root y would be y to the 3/2, minus y times y over 2 would be y squared over 2 dy. So we have these two different integrals, which if we evaluate, would give us the same value, so whatever we have here and here are equal to one another. And we can see for this example, we would probably prefer to use that washer method. Setting up the integral using the method of shells was a little bit trickier because we had to solve for our equations in terms of y, and so it was a little bit more difficult there than the washer method. But nonetheless, we could use either of these integrals to find the volume of that solid. So let's look at one last example for this section. Again, comparing a couple of different methods for finding the volume of a solid of revolution. So here we're asked to consider the region R bounded by y equals cosine of x, y equals 0, which is the x-axis, x equals 0, so the y-axis, and the line x equals pi over 2. And again, set up but do not evaluate integrals to find the volume of the solid obtained by revolving R about the y-axis using either the disk method or the shell method. So let's sketch our region here. We have the graph of, or the region bounded by the graph of cosine x, the x and y axes, and pi equals 2. Or x equals pi over 2. So here let's start by sketching our x and y axes. Now we know that the graph of y equals cosine x intersects the y-axis at 1, since cosine of 0 is 1, and it intersects the x-axis at pi over 2. So in general, looks something like this, where this curve is the graph of y equals cosine x. So we're looking at the region R, which is this little shaded region, and we're told to revolve this about the y-axis. We want integrals for the volume using either disks or shells. Now, if it were up to us, we can see since this graph is bounded above by a function of x, y equals cosine of x, we might prefer to slice this thing up using vertical slices taken at a distance of x units from the y-axis of a thin thickness dx. And we can see if we take this vertical slice and we're revolving about a vertical line, we would be using the shell method. So I'll say here, using shells, the volume of our solid would be found by integrating 2 pi along the x-axis from 0 to pi over 2. Of the radius of our cylinder, so the distance here from our axis of revolution, the y-axis, out to our strip is exactly what we were calling x. And the height of our cylinder is given by the height of our curve, y equals cosine of x, times the thickness of our cylinder, which is what we were calling dx. So this integral would give us the volume of that solid of revolution using the shell method. Now we're also supposed to set up an integral using the disk method. So if I'm revolving about a vertical line and I want to get a disk shape, that means that I would need to slice my region up horizontally, so that when I revolve this little horizontal strip about the y-axis, we see that we would have a solid disk. So here my horizontal slice will be taken at a distance y units above the x-axis, and the thickness of that slice I'll call dy. So if we revolve that slice about the y-axis, we can see that we would get a solid disk. So using the disk method, the volume of our solid is given by pi times the integral along the y-axis from 0 to 1 of the radius of my disk squared. Now the radius of the disk is going to be the horizontal distance that I traveled from the y-axis out to the curve. So if I'm setting up an integral in terms of y, I need the equation for my curve to be a function of a function of y. So solving this equation for the curve for x, I would have x is equal to the arc cosine of y. So the radius of my disk is then arc cosine of y. I'm squaring that radius, and then I'm multiplying by the thickness of my disk, which was dy. So we have these two integrals for the volume of the solid of interest in terms of the shell method or the disk method. Now, if we were to evaluate these, again, we would get the same volume. And looking at these two integrals, it appears that probably the first integral using the shell method would be easier to evaluate than the second, because the first one at least doesn't involve this messy arc cosine function. However, thus far, we have not talked about methods for integrating a function of the form x times cosine of x. That's something that we'll look at when we start our Chapter 3 material, how to evaluate this type of antiderivative.